Okay, today what we're going to do is we're going to learn about capacitors hooked up in circuits. We have two main objectives: to figure out first how to find equivalent capacitance in a circuit connected with 3 or more capacitors. Then we also need to figure out how to find the charge and the voltage across every single capacitor in a complex circuit. So we're going to see some quick notes today, and then we're also going to look at one quick example problem. So the first thing that we need to do is we need to learn how to draw a capacitor, and as you can see on the page in front of you, we have a capacitor right here. If you notice about the capacitor, it looks like two plates connected with wires, which is exactly what a capacitor is. If you remember from notes that we saw before, a capacitor is a device that allows you to store charge, a small amount of charge, until you connect it up to a wire, and then it will discharge. So what we're going to do here is we're going to imagine that we're going to connect this capacitor up to a battery. And so what I'll do is I will draw a battery right here and connect it in series with this capacitor. Now, as soon as I connect this to the battery, we're going to have some current that's going to start flowing. The current is going to flow out of the positive side of the battery towards the capacitor. That current is going to build up a positive charge, in this case, on the left side of the capacitor. And at the same time, it's going to build up an equal but opposite negative charge on the right side of the capacitor. Now, the thing that we saw in class is that as we connect a capacitor to a battery, it will build up charge, but slowly over time, and eventually it will be fully charged. So what we're going to see in this circuit is we're going to see over time the current is going to drop off, and I'm going to show that right here. The capacitor is charging, 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 and then eventually the current is going to drop all the way down to 0, in which case we would consider this capacitor fully charged by the battery. And if you look at this circuit, we're going to see that the voltage across the capacitor is now the full voltage of the battery, and we would be able to use our standard equation of capacitance is equal to Q over V in order to solve for the charge on the capacitor or the capacitance of this particular capacitor. So we have a couple things that we learned here. We know that as soon as you connect a capacitor up to a battery, we see that the resistance at the beginning, R naught, is approximately equal to 0 ohms. But once you leave it connected for a while, that resistance increases and increases and increases until the resistance at a later time is approximately equal to infinity. It has a full resistance, in which case we would consider this capacitor fully charged. And we would be able to use this equation in order to solve for things like voltage, charge, or capacitance. Excellent. So what we're going to do now is we're going to look to see what happens when you take a capacitor and you connect it either in series, as we see in this situation, or if we connect it in parallel to a battery, as we see in this situation. Now, there are some unique sort of similarities between capacitors connected in series and capacitors connected in parallel, and you can think of it like resistors. However, there's some unique differences. What we want to do is we want to look at series first, and we're going to imagine that we're going to run a current from the left side into the first capacitor. Now, what's going to happen is on this first capacitor, we're going to build up a positive charge Q on the left side, which is going to build up an equal and opposite charge, negative Q, on the right-hand plate. Now, the interesting that happens here is we have to think about where is it that this negative Q came from? Where did that charge come from? And if you think about it, that charge had to come from this capacitor, because that's the only thing that is connected to it. So what happens is that some negative electrons flow in the left direction from that capacitor. What that does is that means that this left plate builds up a positive Q. This one has the same negative Q, and so on and so forth in series, so that every single capacitor actually ends up with the exact same charge. So for capacitors in series, what we just learned is that every single capacitor has the exact same charge. Okay? Now, the other thing that we know is that just like with resistors, since this is connected in series, the voltage of each of these individual capacitors is going to add up to equal the voltage of the battery. Excellent. So what we also have is we have the voltage for each of these individual capacitors is equal to the voltage of the battery. Voltage total is equal to V1 plus V2 plus V3. The other interesting thing, which is not like resistors in series, is that the capacitance add up inversely. So the equivalent capacitance of this connection is going to be 1 over equivalent capacitance is equal to 1 over capacitance 1 plus 1 over capacitance 2 plus 1 over capacitance 3, and so on. So in that way, it's very different from a resistor. Now let's come over here and look at our parallel side for capacitors. If we think about current flowing into the left side here, we see that that current can split and go independently to each and every one of these capacitors. So there's no need for the charge to be the same on every single one of these. So in this case, we know that the charge on each one of these capacitors adds up to a total amount of charge built up on all three. And so I'll represent that here as a Q total in these three capacitors is equal to Q1 plus Q2 plus Q3. Now, just like we saw in parallel for resistors, we know that voltage in parallel is always equal. So we know that the voltage for each one of these capacitors, V1, is equal to the voltage across V2, is equal to the voltage across V3. Now, the way we add capacitors in parallel is actually like we add resistors in series, in that the capacitances in parallel are simply just going to add up. And so in this case, we're going to have equivalent capacitance is equal to C1 plus C2 plus C3. Excellent. So there's a lot that's similar here, particularly if we think about voltages. We know that the voltage here works the same in series, and that the voltage here works the same as resistors in parallel. But we also learned that the capacitances are the opposite as what we see for resistors. So what we're going to do now is we're going to look at one example problem where we see all capacitors. So if we look here, we have a 42 microfarad capacitor, which is connected to an 18 microfarad capacitor and a 25 microfarad capacitor connected in parallel. And what we want to do is we want to find the charge and the voltage across each and every single capacitor here. The first thing that we need to do is find the equivalent capacitance. And to find the equivalent capacitance, we want to work with parallel first. So if we look right here, we see that we have two capacitors connected in parallel with each other. So it's actually really easy to add these together. All we have to do is take 18 microfarads plus 25 microfarads, And we find that that section has a capacitance of 43 microfarads. And so what I'm going to do is I'm going to quickly redraw this circuit, and I'm going to replace the parallel series with that 43 microfarad capacitor. Excellent. Now that I have this, it's a simple matter for me to condense this circuit down further and add the two remaining capacitors in series. And I'm going to do that using the inverses. So we're going to take 1 over 42 plus 1 over 43, take the inverse of our answer, and we see that we get 21.24 or 21.25 microfarads. So what I'm going to do here is I'm going to just simply draw this out with one capacitor. And what I'm going to put there is the 21.25 microfarads. And this whole time our battery has been 6 volts. So what we can do here now is we can use the equation for capacitance and voltage to find the charge that is built up on this single equivalent capacitance. So right now what we can do is we can use this equation. C is equal to Q over V to find the equivalent capacitance. Now we have both V and the capacitance, and so to do this quickly, we'll take 21. Don't forget that we have to multiply by 10 to the negative 6, and multiply by the 6 volts. So if we see here, we have a charge that is built up that ends up being 1.27 times 10 to the negative 4th coulombs. 1.27 times 10 to the negative 4th coulombs. Now all I'm simply going to do is back my way through the circuit until I get to the original circuit here. So what I'm going to do is I'm going to look at our second condensed circuit, which we see here. And now I can take the rules that we have and figure out what is the charge on each one of these capacitors. Well, since these capacitors are in series, we know that the charge has to be the same. So both of these capacitors have an equal charge on them, and that is the same as what we found before, which is 1.27 times 10 to the negative 4th coulombs. And using the same principle here, I should be able to find the voltage for each of these capacitors independently using our equation here. So I'll do that quickly and see what we get. So for the first one, it's going to simply be 1.27 times 10 to the negative 4th divided by 42 times 10 to the 6th. I get 3.02. I'm going to round that over to 3. Same thing here. If this is 3 volts, because I can take one loop around this circuit, let me do that right now. If I take one loop around that, I have to add up to 6. So I know that this is also 3 volts. So let's step back over here to the original circuit. I already know everything I need to know about this 42 microfarad. I know that the charge built up on it is 1.27 times 10 to the negative 4th coulombs. And I know that the voltage is 3 volts. Since these remaining 2 capacitors are in parallel, I know that each of them also has 3 volts built up. So here again, it's a simple matter of using our capacitance equation here in order to solve for the charge that is built up on each of these capacitors. So we'll do that very quickly. We'll take the capacitance, multiply it by 3, and figure out the charge. Starting with the bottom, we'll take 25 times 10 to the negative 6, multiply it by 3. We end up with 7.5 times 10 to the negative 5th coulombs. For the top, we will take 18 times 10 to the negative 6th and multiply it by the 3 volts. We end up with 5.4 times 10 to the 5th coulombs. Negative 5th coulombs. And so in a way that's very similar to what we did with resistors, we were able to find the voltage and the charge built up on every single capacitor. Take a moment, watch this video again, pause my explanation at any points to make sure that you understand, and we'll see a quiz on this material when you come to the next class.